This is our final video example for lesson 3B, so our last optimization example that we're going to do together. We skipped example 5 if you're keeping track. We've got a situation where we have two people that live across the river from one another, and one of them wants to go to the other person and can swim at a certain rate and run at a different rate, and we want to know the quickest that she can get across the river. The river is 75 meters wide. So we have all the information we need, and we need to come up with a way to optimize the amount of time that she takes. You may have seen questions similar to this in physics, and we will see questions similar to this when we learn about vectors. So I think it's important to note for this question that we are assuming that any type of current in the river does not affect the rate that she can swim. So she can swim across the river at any angle, and it makes no difference in how fast she can go across the river. So I guess assume that there's very little to no actual current. So what we have here at the right is a diagram of the situation. We've got Paul across the river from Sam. The river is 75 meters wide, and their houses are 180 meters apart, just looking straight down the river. So we have lots of options here. She could swim straight to Sam. And so we could figure that out using Pythagorean theorem and say, well, she swims at 4 meters per second, and she would get there. She could run along the riverbank and then turn when she gets across from Paul and go straight across. And again, we could figure that out pretty quickly. Or she could spend some of the time running and then the rest of the time swimming at an angle. And again, we could figure that out. So there are a whole bunch of different options here, and that's the whole idea with these problems, that there's more than one solution, but we want the one and only solution that gets her there in the fastest amount of time. So in order to start solving this problem, we need to come up with an expression for the amount of time it takes her to cross the river. The total time is going to be the sum of the time she spends running plus the time she spends swimming. So that's what we need to optimize. So if we look at our diagram, what we have here are not actually the times that she spends swimming and the time she spends running. What we have are the distance that she ran and the distance that she swam. So I am going to arbitrarily choose that this distance is going to be x, so this distance that she ran is going to be 180 minus x. We could have done that in the reverse order, so I could have said x is how far she ran, and 180 minus x is the amount that's sort of left horizontally for her to go, but I did it this way because the run equation is the easier one, so it makes sense to use 180 minus x in the easier part of the equation. So the distance that she ran is 180 minus x, and we have to remember from science the relationship between time and distance, so we'll write that out over here. So we will recall from science that the speed she ran is equal to the distance she ran divided by the time she spent running. So we know that the speed she can, what the speed she can run is. We know that that's 5 meters per second. So 5 meters per second is equal to the distance she ran, which is equal to 180 minus x. So 180 minus x over the time she spent going there. So by isolating the time she spent running, we get this expression for the time she ran was 180 minus x over 5. Now we have to do much the same thing for the time she spent swimming. So we're going to start with this distance the distance that she actually swam. We are going to remember that this is a little triangle, and in our triangle we have one side that's x, one side that's 75, and one side that is the distance she ended up swimming. And we want to represent this distance she swam in terms of s. So we can use Pythagorean theorem. So the distance she swam squared is equal to the sum of the other two. So x squared plus 75 squared. So we end up with this expression. The distance she swam is the square root of x squared plus 75 squared. And then using the same method that we did down here to isolate the time she spent running, we're going to figure out the time she spent swimming, which will end up being the distance she swam divided by the speed she swam, which we have here is 4. So we end up with the square root of x squared plus 75 squared, which is the distance she swam, divided by how fast she swam, which is 4 meters per second. So now, after all of that, we have an expression for the total time in terms of one variable, x, and x is this amount, sort of an arbitrarily chosen little distance that we had on our original drawing. So we figured out an expression using only x, and now all we have to do is get the derivative of that, set it equal to 0, and solve. So here's our equation again. The first thing we're going to do is find the derivative at x. So at this point, on the first yellow step, I just got the derivative. In case you're wondering what happened, I thought of the divided by 5 and divided by 4 as coefficients of 1 over 5 and 1 over 4, which makes getting the derivative much simpler. If you didn't notice that, you could have used quotient rule and you will still end up with the correct answer in the end. The second yellow step was just simplifying a little bit. So grouping together the 1 over 4 and the 1 over 2 and the 2x, and moving the negative 1/2 exponent into the denominator where it becomes positive 1/2. So we end up with this fairly simplified equation, and we're going to set it equal to 0 in order to figure out the turning points. So the easiest thing to do, in my opinion, here is move the 1 over 5 to the other side. And then we end up with something that we can cross multiply. After cross multiplying, we're left with this, and this is still kind of messy, and we have this to the power of 1/2, so we're going to isolate that. And if you would prefer at this point to think about it as a square root sign, that might be helpful, because our next step is going to be square both sides to get rid of that square root sign altogether. Working that through. And I just realized we forgot the x, so just add that in. And then we just have to group the like terms with the x squareds, and we're almost done. So the first step here is just to move the like terms to the same side, and then actually do the subtraction. And finally, isolate for x. Which gives us in the end an optimal value of plus or minus 100. So if we flip back to what the question said, we remember that x was this amount in the diagram that she's going to, well, 180 minus x was the amount that she was going to run. So it doesn't make sense for x to be negative, so we only have to worry about the x is equal to 100. That was our optimal value. So if the optimal value is x being 100, it means she's going to run for 80 and then swim the rest. So if we actually want the that she can meet him, we're going to plug 100 into that equation, the original time equation. So if we do that, the answer ends up being 47.25 seconds. So that is the fastest she can meet him. And that is the end of that problem. Thank you very much for listening.